And you are at RII's last webinar of 2024, Maximizing Yields of CO2 Enrichment, Best Practices and Emerging Technologies in CEA Operations. This is one that I've wanted to do for quite some time, particularly when we published our best practices for controls and automation and had some great conversations with David Goodnack on how to make the chapter on CO2 controls much better. So I figured there's a lot to learn here. Okay, we're going to go ahead and get started, and some more folks are going to roll in. I'm Rob Eddy with RII. I'm the horticulturalist. Joining me today is Brenna McMillan. She'll be assisting me in coordinating all of the technology. This is the presentation on maximizing yields with CO2 enrichment. You may have seen this if you're in the waiting room. Our good friends over at Urban Ag News are doing a grower questionnaire on how to use CO2 in your CEA facility. So please fill that out if you're a grower. Brenna will put the link to that in the chat. And that reminds me to tell you that if you have questions during our presentation today, put that into the Q&A, and we will answer it either in writing. Our panelists who are not speaking might answer it for you, or I'll answer it for you. Or if we don't get to it, we'll get to it at the end when there's a discussion session. As a reminder, what it's all about, hey, CO2 is part of photosynthesis, okay? See, the leaves absorb CO2 from the air, and the plant absorbs water from the roots and combines those in the presence of sunlight or artificial light, and with chlorophyll converts that through photosynthesis to glucose and oxygen. And those are the building blocks for all of the good stuff that plants make: the DNA, the proteins, the flavonoids for flavor, the terpenes for aroma, and of course, biomass yield. So that's what it's all about. And it turns out you can kind of cheat a little bit by giving plants more CO2, and they crank out more of the good stuff typically. A lot of what you'll hear today was from our best practices guides on control and automation, which was released in May. That's a free guide. Brenna will put the link to that, to our catalog at RII. And you can download that. And there's a whole section on CO2, along with lots of other ways to improve resource efficiency at your facility using controls and automation. That working group was comprised of universities and industry folks, and some utility members and some government members. It was a great group, and we just want to acknowledge them all for their hard work on that best practices guide. What we're working on currently, just for the fun of it, is let you know that we're working on one on AI and advanced robotics, and that will come out towards the end of the first quarter of 2025. So this controls automation is kind of a precursor to the AI and advanced robotics. Okay, enough about myself. I'm going to have our subject matter experts introduce themselves. I'll start with David Goodnack, and we'll go to Camille and then Dick. Go ahead, David.
Hey guys, I'm David Goodnack. I'm the owner of Plant CO2. My background is engineering and automation systems, and I've been working in the CEA industry for the past 6 years at different automation companies. My last one was GrowLink.
Great, thank you, David. Camille?
Good morning, everyone. My name is Camille. I have spent the last 8 years of my career working actually in the fresh produce industry in agricultural technology. My role at Skytree is leading business development in North America, so Canada, United States, and Mexico.
Excellent. Thank you, Camille. Great to have you here. Dick?
Hey, good morning, everybody. My name is Dick Kramp. I'm 30 years active in the greenhouse industry, cogeneration business, installed more than 1,500 systems across the world, not only supplying power and heat, but also CO2 to the greenhouses.
Great, thank you, Dick. So as you can see, fantastic subject matter expert panel covering the broad range of CO2 use in CEA. So I'll jump into it. I'm going to turn it over now to David Goodnack for his presentation.
Perfect. Go ahead and just go right to the first slide there. as I mentioned, the last company I was with was GrowLink. This is important because I started the company, Plant CO2, while I was at GrowLink. My role there was to make sure that all of the different systems integrated correctly. And when it got to CO2 and people asked me about it, I didn't really have any recommendations. I could give them 10 lighting companies and HVAC companies. When it came to CO2, there was a huge knowledge gap what traditional CO2 vendors were able to supply. Traditionally, CO2 vendors were trying to supply the bulk CO2 tank, and it may be a couple different life safety components, but really not the full system. So what I want to do is walk through this. So for a liquid CO2 system, which I specialize in, on the left, you have the bulk CO2 tank, which holds roughly a month's worth of CO2 plus 25% reserve. So once they fill it once a month, there'll be 25% in reserve. The main line there is going to go through the facility, typically down the hallway with lines that drop down into each room. So this is an example of one room here. It drops down. It has a CO2 enrichment manifold, which is key to being able to precisely control and dose CO2 into the space. The line from the outlet to the HVAC duct, this is one way that we can distribute CO2 within the space. So if we're looking at kind of a good, better, best, when we're looking at distribution, I would say good would be injecting into the HVAC duct. Most people do it this method. It's one of the easiest methods to inject CO2. However, you're kind of showering and trying to fill the entire cubic volume with CO2. Better would be when you're injecting CO2 into a vertical airflow system, like a PIP VAS system, where the air is coming from top down within the rack for an indoor facility. Best, in my opinion, would be a under canopy airflow system. This is blowing air from underneath the canopy, blowing it up. It's disrupting the little micro boundary layers, as well as distributing CO2 exactly where the plants are going to be trying to absorb it. So you want that to be the highest concentration. The rest of what you're seeing on here, you're seeing the life safety system off to the right-hand side. This is the safety sensor that's 12 inches off the ground, the horns and strobes, which are required to notify people inside the building, and as well as power and relay. That's for integrating to be able to control the exhaust purge fan, which is required, as well as the safety isolation valves, which you see at the tank, number 1, and in the room, number 2. So this whole system is going to apply as well to Camille, which is the Skytree portion. She'll just tell you the difference between my bulk CO2 tank is for liquid CO2. Hers will be more of a day storage tank for the gas that her unit produces. You can go to the next slide. So when we're designing CO2 systems, one of the most important things you can do is size your system correctly. So having a good CO2 usage calculator is key. This is one of the biggest improvements I made when I joined this industry. The traditional CO2 vendors would come in and kind of give you the tank they had in their laydown yard. So for them, they would always size up and not really worry about exact sizing, just based on what they had. So when I'm sizing, I'm looking at the square footage of the room, the ceiling height, that gives you the cubic volume of the space. I'm looking at how many tiers, vertical tiers of plants you're using to figure out the plant consumption piece of this. How many hours the lights are on, as well as the CO2 target concentrations you're trying to hit. This calculator is really just for me trying to size the tank. This is not your exact usage, although it does get pretty close. Every time I get CO2 data in from customers, I'm always refining this, trying to make this more accurate. So inaccurate tank sizing, I can't stress this enough. I just had a big multi-state operator with cannabis. They were provided a 30-ton tank. I did the calculations after the fact. They needed a 6-ton tank. The difference for that one facility was $45,000 a year just in equipment lease pricing. So it is a big deal to not to size this accurately. Go ahead to the next slide. So let's talk about liquid CO2 and where it comes from. So liquid CO2 is a byproduct from big chemical plants. So typically comes from ethanol, ammonia plants, hydrogen plants, or it could come from a well. So it can be pulled straight from the ground. So understanding this helps understand where we get shortages from, where the pricing of CO2 comes from. CO2 comes in different grades as well. So when you're getting quotes for CO2 or looking for CO2 for your facility, make sure you're asked what grade the CO2 is. Everything plant CO2 offers is beverage grade CO2, meaning it's 99.9% pure. That's less important from Camille's standpoint because she's pulling CO2 from the air. Mine's coming from an ethanol plant or an ammonia plant or something like that. So that 0.1% will be, probably a chemical you don't want. So it's a little more important, the purity when it's coming for liquid CO2. If you get something that's like a welding gas or industrial gas, it's going to start corroding your components, your piping, things like that. So you don't want those additional impurities in there. So when do shortages occur? Because CO2 is a byproduct, when a ammonia plant or something like that shuts down for maintenance, which they do, a planned maintenance once or twice a year, they don't care if the, ethanol plant next door is also going to go down, which shuts down CO2 for a very large space. You'll see that on the next slide. So this is when they come and say something like a force majeure. This will be an all CO2 contract saying, hey, if we do, we run out of CO2, we're going to say force majeure, which means we're going to give you an allocation, meaning we might give you 25% of what you typically get. So imagine that for your facility and the impacts that could have. Go and go to the next slide there. So the next slide is transportation. So these are all the CO2 producing facilities. This may not be everything, but you can kind of see it's not well spread out across the whole US. So if you have a facility in Oregon or something like that, and you're wondering why you might be paying 40 or 50 cents a pound versus 20 cents a pound in Illinois, this is why. The cost of CO2 is almost the same for everyone. Only difference is if Airgas owns that facility, that might be a little bit cheaper or something like that. But when we buy CO2 from a facility, it's 3 cents a pound, something like that. All of the cost of CO2 comes into the transport. It's the trucks, it's the driving, it's the hazmat ratings, it's paying the drivers, the insurance. All of that is where the price of CO2 comes in. But yeah, everyone gets the CO2 from the same places. So one recommendation when you're going out and trying to competitively price CO2, I would not tell the other vendors that you are getting other prices. What happens if you get a price from one vendor and tell vendor two, I've already have a price for CO2. These guys are going to drop the price by 10 cents a pound or something. And you're going to say, wow, that's really good. And they lock you into a 7-year contract at a loss for them. And then they ratchet your price up. So within 6 months or a year, they will be at the other guy's price or more. So you kind of got to go with a trusted vendor. This is kind of feels like cable internet where they get you in at the low price and then they have you there and they just start ratcheting your price up. So go with a trusted vendor. Plant CO2 particularly, we charge what we need to initially so that we don't have to play that pricing game because no one likes it. Yeah, that's all I had for that slide. Go to the next one. So types of tanks. You see 3 different tanks here. The tank on the left, there aren't many new tanks like this being produced. This is a single wall tank that holds the liquid CO2 that is covered in an insulation. Could be a foam insulation, could be a insulation you find in your house. These are very inefficient, and that's why you see that big enclosure on the front. That's a big refrigeration unit. So these things are cycling on all day long to cool the CO2 in that tank to make sure it stays a liquid. Once you hit 350 PSI, these tanks typically start venting off the gas to make sure it doesn't go over the max operating of the tank. So make sure if someone's providing you CO2, you ask, what type of tank are you providing? Does it have a refrigeration unit? Does it require electricity? These are things that are hidden costs that you don't know about initially. The tank in the center, this is a new style vacuum jacketed receiver. So these style tanks are called receivers. They require a electric vaporizer. They don't have any way of turning the liquid to gas with the tank itself. So there's an electric vaporizer. It is lifted off a special truck with 2 cranes, rotated in place, and set down on a special designed structural pad. These are typically 3 feet deep with rebar inside. It needs permitting, structural. So typically the setup and install of this costs around $30,000. The tank on the right is what Plant CO2 specializes in. This is called a Permax tank. It comes on a structural skid. That's the skid you see on the bottom. So it's shipped on a flatbed truck, which is much cheaper. You can lift it off with a forklift and set it in place. This doesn't need to be on a structural pad. You don't need permitting for that. You just need either a gravel pad or a piece of concrete that's just flat to set this thing on. So this style tank, it's probably 95% of the applications I size out, and it saves you roughly $30,000 on install costs. Go ahead and go to the last slide for me. So liquid CO2 versus other technologies, when we really look at it, liquid CO2 is very simple. It's very reliable. So it does have some downsides as far as cost, but you can't beat the reliability of it. Your truck shows up and delivers it. It dumps liquid CO2 in a tank. That tank lasts for 50 years. There's no maintenance there. The only maintenance really associated with the tank would be the pressure relief valves, which it has redundancies all over. So if one goes bad, you shut it, keeps going until someone shows up to repair it. The stuff inside the facility, it's clean, pure, beverage grade CO2, and it has a very low capital cost, meaning the initial cost is a tank shows up and then you start paying rent on it as soon as it lands. The cons, prices increase every year for CO2. That's a given. Stuff will keep going and getting more expensive. CO2 shortages can occur. Most vendors will, if there's a CO2 shortage, they'll say, hey, we're going to give you 25% of what you typically use. That's all. Companies that I work for, they will truck it in from 3 states over to make sure you never go without CO2. So there are companies that will do that. You will pay more, though, in those moments of force majeure. And then ongoing equipment rental. Once you have a tank on site, you're always going to pay that rental, whether you have it for 10 years, 20 years. So I'd say that's a downside as well.
Great, David. Thank you. I do have a question for you. Because you finished right on time. Thank you. Awesome. First, I want to remind the audience that you can ask questions in the webinar chat, and we'll get to those either at the end of the program or one of our panelists might answer it in the meantime. David, where is the line between what the company like you would be providing, like when we think about the tanks, and then the distribution system inside the greenhouse? Who installs that, and where do the two meet up?
You want to go to slide 1 for me real quick? Sure. Yeah, perfect. So this started out with Plant CO2 just manufacturing that CO2 enrichment manifold where no one did, and it slowly grew to be a full scope provider. So I can provide the tank, the supply, the CO2 distribution. I provide kits for that. So I design those kits. It's all low density polyethylene tubing that's meant for CO2 and those pressures. And it has kind of quick connect, kind of like doing PEX tubing in your house. If you've ever done that, it's just push in kind of like a shark bite. So it can be self-install based on the kits that I design. You mentioned greenhouse specifically. Rarely is liquid CO2 found in greenhouses because you're going to find that when Dick presents his stuff, that it's typically a boiler system or something like that where they're pulling CO2 off the gas. I do have this for retrofit systems though, but greenhouse systems, not so much. I mainly do indoor. I will do greenhouse, but yeah, I can help with the whole life safety design, the distribution design, all of that. We don't do install because it doesn't make sense to ship copper piping or, if you've got local plumbers, local low voltage techs, it's always a cost savings if your guys do it on site.
That's great. Thanks for answering that. And also, I mentioned I really enjoyed you talking about using it to distributing it sub canopy and pushing it up through the crop, because it seems like the science backs that up. Next, we're going to have Dick Kramp with his presentation. Go ahead, Dick.
Okay, next slide, Rob. So Dick Kramp, I'm with AB Energy USA. I'm leading the Global Center of Excellence for AB. More than 30 years of experiences in that field, being involved in all the major developments in greenhouses across the world, where there is a need for power, or the power is too expensive from the grid to be substituted by a CHP system. Next slide. So business as usual, a natural gas boiler producing heat and CO2 for the greenhouse, with a greenhouse that is lidded or unlidded. Electricity from the grid and liquid CO2 is trucked in. We are seeing more and more that basically liquid CO2 is being used to top off when semi-closed greenhouses are totally closed. Then you see that growers are stopping dosing CO2 from boilers or CHP, but then adding liquid CO2 to their greenhouses, because of the ventilation in the greenhouse should be at a certain level to use the CO2 from the boiler or from the CHP unit. Next slide. So basically what we are doing, we are taking the natural gas, because our systems run on natural gas or can in the future run on renewable natural gas. What would be a great future, but for now, renewable natural gas with all kinds of alternative gases are too expensive to run on, because, you know, it's like gas that is basically used and bought by large corporate companies that are using it to reduce their carbon footprint. And for the greenhouse sector, as we know, every penny counts. So natural gas is still way more cheap than renewable natural gas. And that's why it's used in a large scale on natural gas. So the natural gas is going through the engine. The engine is producing heat, CO2, and electricity. The heat, CO2, is going directly into the greenhouse, and the electricity can be either used in the greenhouse to power the grow lights, or can be supplied back into the grid and to sell it to the local utility or the grid regulator. There's still a natural gas boiler, because when you want to be high efficient, the engine is following the heat demand of the greenhouse, so to avoid destruction of heat and to reach the highest possible efficiency. So the boiler is there also as an insurance premium. When there is something wrong with the cogen, then there's still a boiler to heat the greenhouse during the winter time. Yeah, next slide. So what makes CHP so attractive in the CEA sector, and why it's so widely used in the world? For example, in the Netherlands, there is around 4 gigawatts of cogeneration installed at greenhouses, because of the whole environment for CHP was really paved for the growers by the government and by the industry itself. So it's a simultaneous supply of heat, cooling, electricity, and CO2. So the CO2 basically is coming for free, because, you know, you're offsetting the boiler by producing the heat. You can use the heat and absorption chillers to make cold, and you can sell the electricity back into the grid to create an additional income stream. So the CO2 is basically a waste that comes for free. Power generation where loads are. So we are maximizing the energy efficiency. As I said, we are following the heat demand of the greenhouse. And the thermal energy produced can be stored in large heat storage tanks. So we can run the cogen during the day when there's a big need for CO2 in the greenhouse, or the electricity prices are very high. And then there's no need for heat. We can store it in a tank, and we can take it overnight to heat the greenhouse. When you size it as such, then the system efficiency on LHV, lower heating value of the gas, it's larger than 90%. We have reached even projects in the US that are going in the direction of 95, 96%. So every MMBTU that we burn, more than 90% is used in the greenhouse. CO2 is captured during this power production and will be blown into the greenhouse. And again, you know, the CHP has been so successful, especially in the Netherlands, by creating an additional income stream by selling power to the grid, or offset expensive electricity from the grid, securing the spark spread. It is very clear that without CHP, the Dutch greenhouse industry would not have survived the high energy costs that they were facing. When the gas price rises, normally also the electricity price is connected to this. So when the gas price goes up, the electricity price goes up. So the Dutch greenhouse industry, they are really the balancing tool for the grid regulator in the Netherlands. 9% of all the natural gas in the Netherlands used goes to the greenhouse sector, but they are producing 11 to 15% of the needed electricity in the Netherlands, and that is dispatchable power, right? So it's maximizing the use of renewable assets because they are very volatile, and the greenhouse sector is helping to reduce the volatility of the grid. Next slide. So already talked about this carbon dioxide, how important it is, increasing the amount of CO2 into the greenhouse will create an additional yield. Although we are seeing great developments in the greenhouse industry where less and less CO2 is used in the greenhouse, that's a good thing. And also we see a lot of developments like Camille is presenting by capturing CO2 with other technologies. Next slide. What can be a great combination with CHP, by the way? So our system is based on a catalyst. So the exhaust gas is going into a catalyst where we are reducing ethylene, because during the combustion process, it could happen that there's unburned hydrocarbons that is reduced by the oxygen section of the catalyst. And then there is a NOx section, the SCR section, that is reducing the NOx going into the greenhouse. Basically, this system is completely controlled. It's using urea to reduce the NOx. And it has a guarding system called co-detain analyzer that is guarding the emissions coming out of the catalyst to be sure that there is no harmful gases going into the greenhouse. That can either give a problem to the crop. Next slide. So to compare a boiler versus a CHP system, so sorry for my European standards, but basically when you put 100 kilowatts of fuel into a boiler with a 95% of efficiency, you get 95 kilowatts of thermal power, and at the same time 18 kilograms of CO2. So the success in the Netherlands by having CHP was basically with a CHP unit, you could produce electricity with an efficiency of 44% and a thermal efficiency of 50%. So to get the same amount of heat, the 95 kilowatt thermal, by a CHP unit, you have to put in the double amount of gas. By putting in the double amount of gas, you're getting 100 kilowatt thermal of heat that you can use in the greenhouse. You get 88 kilowatts of electricity that you can use for your grow lights or sell back into the grid, and you get the double amount of CO2. Next slide. So with the double amount of CO2, and you can see here the productivity graph, theoretically, that you see that the increase of the amount of CO2 in the greenhouse will increase the productivity of the crop. And it's different from each and every crop. It's different from each and every greenhouse that you're using. I have to tell that we are working solely with greenhouses, which has a ventilation ratio. We are not working with indoor farms because there is no air exchange in the indoor farm. And that is where David comes in with his liquid CO2 that is basically food grade. This CO2 is not food grade. It's good enough and proven in the greenhouse industry. And it's very cheap to create. And basically it's coming for free from the engine. Next slide. So there's a lot of offense against natural gas, but basically without CO2 to reach the same production in the greenhouse, it has to be X size bigger to have the same production without CO2, right? So CO2 is now trapped in or created by burning on-site natural gas. The least carbon-intensive power production is on-site CHP. When we compare a kilowatt hour bought from the grid, even in California, decentralized power is less carbon intensive than buying a kilowatt hour from PG&E or other utility companies. Because it's the decentralized concept, you're producing everything on site. Also, the CO2 that doesn't have to be trucked in is available from the CHP. At the same time, the gas grid is becoming greener because we also supply biogas upgrading systems, that is upgrading biogas to renewable natural gas. So the gas grid gets more and more greener by the injection of renewable natural gas into the pipeline. CHP using greener gas is still the best technology and the highest total efficiency, higher than 95%, what I said. Today it's possible to source RNG to be virtually used in the CHP unit, but, to become carbon neutral. But as I said, RNG is still extremely expensive, like green electricity is extremely expensive. Governments and policymakers should support greenhouses to get RNG for a reasonable price to secure a nation's food production and to secure grid stability. Next slide. So we are also working on some other pilot projects that we are doing. And this is a project in the Netherlands where we are not using a catalyst system, but we are using an amine system where we are absorbing the CO2 into amine fluid and basically getting it out by reheating the fluid, and the CO2 that comes out of the system is stored into big balloons that can be used in the greenhouse. This technology has been used many times in the food and beverage business. We have done projects for Coca-Cola, Pepsi, where we are using and big other beverage brands, where we are going to produce food-grade CO2. It was still not affordable for the greenhouse industry because the capital expenditure for this kind of system was very high. But nowadays that the liquid CO2 is becoming so expensive, it starts to make sense again. Next slide. So you can see here the technology where the exhaust gas is going into the absorption column. The absorption column is bringing the fluid into the stripper, where we are reheating the stripper with the heat that comes from the CHP, and we are damping out the CO2 out of the fluid, where we later on can also compress it to make liquid CO2. We are now offering this for a couple of data center projects that we are doing, where we are combining greenhouses with data centers. So this is the end of my presentation, but I wanted to address that CHP is not only there to supply, free CO2, but it's the biggest success of the CHP units in the Netherlands was covering the heat demand, covering the CO2 demand, and creating an additional income stream for the growers by selling power back into the grid. Sometimes we say they're making more money with selling power back into the grid than picking tomatoes. Thank you.
Thank you, Dick. Fascinating stuff. Before we move on, I want to remind the audience that we're putting the emails for our subject matter experts in the chat as they speak. So if you want to follow up with them with questions, we'll also show them at those emails at the end. Next up, we're going to have Camille. Go ahead, Camille. The mic is yours.
Fantastic. Thank you. We can just go to the title slide. Yeah, we'll just hang out here for a moment. I just want to start by saying I'm very excited that CO2 is the subject that we're discussing today, because I think it's very often discussed in kind of a negative context. It's a driver of global warming, climate change. There's too much of it in our atmosphere, which is very true. But I think a lot of people don't realize that it's actually, a very crucial input to many industries, keeps businesses operating. Coca-Cola, Pepsi, they need it for, their drinks. It transports organs from hospitals, and ultimately it's added into greenhouses and vertical farms to increase plant productivity. So It's a really crucial resource, no doubt. There's a reason why, David, Dick, and I are all working for companies, that revolve around this subject. And I think in an industry like controlled environment agriculture that's been around for a very long time, the CO2 supplementation options have been very limited. It's generally CHP, boilers, or liquid CO2, like we've discussed so far. There are some other circular CO2 solutions like biogenic CO2, which uses organic plant matter to create CO2. But the reality is that there's just not enough biomass in the world to completely rely on that as, a source to fully replace fossil fuels. So that's really all to say that I don't think there's one silver bullet, in solving the CO2 supplementation challenge and actually improving the sustainability of it. But I do think that, direct air capture plays a very important role among, these other technologies that David and Dick just talked about. So with that, we can jump into the next slide. Who is Skytree? Skytree is a Dutch company. The technology that we manufacture was born out of the European Space Agency. So as humans, we breathe out carbon dioxide. If you're an astronaut that's up in space in a really small room, there needs to be a way to pull the CO2 out of that room. And that's really where our technology was born. It's a 10-year-old company. So the first 8 years were really spent on research and development, figuring out the right capture technology, optimizing the unit. And then the last 2 years were spent on actually designing and deploying the world's first out of the box, small direct air capture unit, which is called our Cumulus unit. And we'll talk a little bit about where it is in the world today. But ultimately, we're from the Netherlands. We are establishing a pretty large presence here in North America. We're opening our office today in Toronto. It's where I am. And then we also have an office in Nashville. So 6 people total over here in North America because this is such an important market to us. And as a company, we're, really setting out to enable what we're calling a CO2 transition. So we talk a lot about the energy transition and moving towards low carbon emitting energy sources. And we believe that we need to do the same thing with CO2. So replacing fossil fuel-based CO2 with circular CO2 sources, and ultimately removing historic emissions from the atmosphere. And that's when you talk about carbon removal, which is when you get into the carbon credit world, which we won't talk about today. We'll just focus on the utilization aspect of this. But if you go to the next slide, David kind of took us through traditional liquid CO2, where it comes from. I'm just going to go a level deeper on that to talk a little bit about, why this is a bad practice when it comes to the sustainability aspect of this. So you have a large emitter like an ammonia plant or, fertilizer factory. It's giving off CO2 in the manufacturing process, capturing it, liquefying, purifying, and then you're driving it to an agriculture facility. And the plants absorb the CO2. Eventually they die, people eat the plants, but the CO2 still ends up back in the air. It's not a permanent removal. So what's happening in this process is you're postponing emissions. It's not being permanently removed from the atmosphere. And what's worse is that in this process of the purifying, liquefying, and transporting the CO2, you're often amplifying emissions as well. So it leads to amplified and postponed emissions. What direct air capture can do is, when you're actually supplementing CO2 from direct air capture into a grow room, the plants will die, people eat the plants, ends up back into the air, but then you're pulling it out of the air again, right? So that's where that circular CO2 supply comes into play. And in often cases, you can make it a neutral emission, of course, depending on the energy source. But this is, an example of where you can move towards a more circular supply of CO2 and enhancing the sustainability and carbon emissions profile of some of these agriculture facilities. You can go to the next slide. David also set me up for this slide as well. And to me, it's very ironic that, we have all the CO2 in the atmosphere, but yet we're still experiencing CO2 shortages. So this is mostly a result of these plant shutdowns. I just spoke with someone in Toronto, 2 weeks ago, and they mentioned that their gas supplier declared force majeure and they weren't getting CO2 that week. So it's very problematic. It's happening in Virginia, Pennsylvania, other parts of the world, Australia, New Zealand, and this is going to continue to happen. And this is where, it's really important and highlights the importance for growers to have, a portfolio of solutions and alternatives to what they're typically using. One more point on this, in addition to these plant shutdowns, what a lot of these large emitters are starting to do is actually divert their supply of CO2 to be stored permanently. There's an example of this happening in the Netherlands where, CO2 that's being supplied by Shell is going through a pipeline to greenhouses. Shell's diverting that supply to go to the North Sea. It's being sequestered permanently under the North Sea, which means there are going to be shortages in that CO2 pipeline, which is actually a project we're participating in to build direct air capture hubs along that pipeline, as an alternative source of CO2 that they can get directly from the air. You can go to the next slide. Without, won't belabor the fossil fuel-based CO2 point too much, but in addition to what I just talked about around, these traditional sources, there's a lot of volatility happening with CO2 prices and gas prices as the demand for CO2 goes up and the supply goes down. Of course, that drives prices up. In some places, there are policy changes happening where natural gas is actually being phased out. It's happening in the Netherlands. Electric systems cannot create CO2, so there needs to be, some solution to have CO2 that's affordable, to actually bridge that gap. And ultimately, the CO2 is drying up in many cases. So direct air capture, in our perspective, is really crucial in maintaining the CEA industry and making sure that vertical farms and greenhouses can stay in operation. Next slide, please. So direct air capture really kind of solves three problems. Firstly, you have certainty of supply. So, you don't have to deal with, not receiving your delivery of CO2 that week, or there being a potential shortage. The CO2 is coming directly out of the air, so you have it when you need it. There's not volatility in the CO2 prices, so it's relatively stable, and you have visibility into those costs, for the foreseen future. And of course, lastly, it's sustainable CO2 production. So like we've covered already, it's that circular CO2 supply, which is very important, especially in the CEA industry. I see often that vertical farms will come out with these LCAs and they don't even include CO2 in the LCA, which is astonishing to me. But when you consider CO2 and you can make these changes, around circular CO2, I think the benefits will be felt pretty greatly in terms of, the emissions profiles of some of these facilities. Next slide, please. So Cumulus, I mentioned this is the first unit that we've produced. It is deployed in 5 locations. We have a couple in the Netherlands. One you can see on the right-hand side of the screen here is with the Wageningen University. So they're doing a study right now where they're comparing traditional CO2, liquid CO2 to direct air capture CO2 on the growth of cucumbers. That's ongoing. We will be releasing results of that very soon. Koper Cress, another partner of ours in the Netherlands. We do have a unit in Canada with Fieldless. We have a unit in Spain and Belgium, and we will be delivering our first US system actually in Pennsylvania in January. And of course, we will deliver more of these units. But This unit is basically focused on having a fixed bed sorbent. So what that means is you have a unit, it's about the size of like a large American refrigerator. You pull air through that unit, and inside there's a cartridge that has a sorbent on it. That sorbent is actually what the CO2 sticks to. And then when you're ready to release the CO2, you actually have to heat that sorbent up. Releases the CO2, and that can get compressed into a buffer tank. Again, like David mentioned before, it's not delivered in liquid form, it's delivered in a gaseous state. But when you get into our bigger units, you can actually start to talk about liquefying that CO2, which can be, compressed into smaller canisters if that's a desire to that specific operation. You can go to the next slide. So talking about these bigger units, that unit does about 30 kilograms of CO2 per day. 20 now, it will be 30 by the spring of next year. And then we have our Stratus units, and these units produce up to a ton of CO2 per day. So when you talk about greenhouses that have a very large CO2 requirement, one of these units, the 1,000 kilograms per day, serves close to a hectare of greenhouse. So that kind of gives you an idea of how much area these units cover. And the great thing about our Stratus unit is that we actually have two versions of it. So we have what's called a hybrid version, which runs off of both waste heat and electricity. So if you have hot water running through your greenhouse, from a boiler, from your heating system, you can actually use that hot water to facilitate that heating of the sorbent, which brings electricity consumption down. And we have the electricity consumption listed here on the slide.
Sorry.
That's okay. And then we also have an all-electric version if waste heat is not available. So both options, just again, depending on where you are in the world. If you have renewable energy available, the electric option is a great option, but it does give you some flexibility. And in terms of how this unit differs from the Cumulus unit, we actually have what's called a moving sorbent inside of this unit. So it's not a fixed cartridge like in our Cumulus. The sorbent is actually going through these adsorption and desorption processes simultaneously. So it really improves the efficiency of the unit. And I do just want to note, I think when people think of direct air capture, they think of a very high electricity consumption and high cost. And we are very focused as a company to innovate on our sorbent specifically, so improving the efficiency of our capture material, which will bring down the electricity consumption per kg significantly. So between now and 2027, we expect to bring that electricity consumption down to closer to 1.5 kilowatt hours per kilogram of CO2. The only thing that's going to get us there is, of course, this scale and this innovation on the sorbent, but we are well on our way to do that. You can go to the next slide. So when it comes to implementing direct air capture into your operation, we do have a couple of options to give growers flexibility. We have a purchase outright option. You can purchase and own the units yourself, or you can lease the units. We have 4 and 6 year lease options. And then we also have CO2 as a service, which is a new business model that we're offering, where essentially you have an offtake contract with us. We finance the units. You commit to purchasing a certain volume, and you pay a certain price, like a fixed price per kilogram of CO2. So a couple of different options, depending on what fits best within your operation, also depending on where you are in the world and how much CO2 is. One option could be better than the other. And we are actively selling our Cumulus units. We are also actively selling our Stratus units. The first Stratus units will launch in the Netherlands with 4 Dutch growers. They will be the very first to roll this out in the spring of next year. And we will be running a very similar program actually here in the United States and in Canada. And I think that's the last slide that I have. Would love to talk to you more about direct air capture. Again, really appreciate the time today with Resource Innovation Institute. Please reach out if you have specific questions. This email is actually incorrect. It should be .us. So that was my mistake, but I think the correct one will be posted in the next, or maybe at the end of the presentation. So thank you, everyone.
Thanks, Camille. And yes, that Camille's US email is in the webinar chat. It'll be on the last slide of this presentation. And that was really fascinating stuff. Thank you, Camille. I'm going to move on to the question and answer session. We got some great questions from our audience, and I really greatly appreciate that. I'm going to stop the share. All right. Great. First question is, and I'm not sure who it'll go to. Let me reread it again. Are there any operations that are co-located, a CEA facility next to a digester or cement facility to offtake the CO2? Do any of our panelists have any insight on that?
Yeah, I can tell something about that. We have done some projects that are close to biogas facilities, but it was always a challenge because of the cleanness of the biogas, and a lot of growers do not want to have a poultry farm or a dairy farm next to their greenhouse because of contaminations, right? And that could be an issue. We have done a couple of projects in Germany where there are a lot of biodigesters, but you have to be extremely careful because the catalysts that are scrubbing the exhaust gas itself have to be very free from contaminations in the gas, because otherwise the catalyst can be damaged. And that happened, when there was not a secured quality of the biogas. What we are seeing right now is that, especially with the biogas upgraders, when there is a membrane system where they're upgrading biogas to, let's say, a renewable natural gas, the off gas in that process is food grade CO2. And that can be liquefied, and then you can transport it without any problem. So this is one of the things that we are working on right now with our R&D department, looking at this kind of solutions. But with CHP itself, you see a lot of greenhouses that are co-locating next to a power plant, but it gives a lot of issues. You saw the big greenhouse of Howlings I think it was in Utah, where he was next to a power plant, and then the power plant gets out of operation, and they're not getting the CO2, or they're not getting even their heat. So basically, it's always a challenge to connect it to an adjacent technology that has other belongings than you have as a greenhouse.
Thank you, Dick. Any comments from Camille or David on that co-location? If not, we've got other questions.
I don't have anything to add, no.
Okay, thank you. All right, next question is, and I believe this was during Dick's presentation. Someone asked, what's the use efficiency of the CO2 dosed?
I'm happy to take a stab at this. When I do my CO2 calculator for estimating CO2 usage in facilities, the biggest user of CO2 is actually not the plant consumption. It is the leakage out of the room, the leakage from the inefficiencies in the HVAC system. So, yeah, it's tough. Sorry, what was the exact question?
It was the use efficiency of the CO2 dosed.
Yeah, we've actually got a guy on this call, I think, that did a PhD paper that I just read yesterday on an airplane, that covers the maximum efficiency of CO2, as well as when the light saturation levels hit and the CO2 usage. So there are much smarter people on this than me.
Yeah, Anton was the person who answered this question. Maybe he could do a follow-up question in the chat.
But again, Rob, what David is saying is correct. It's depending on the kind of greenhouse. Also, plants are emitting CO2 during the night. And then, greenhouses where they recirculate the CO2 are having less usage of CO2. But basically, what I've learned is that from the amount of CO2 that we blow into the greenhouse, I think around 20% is taken by the plant, and half of it is emitted again during the night. And we dosed huge amount of CO2 in the past in the Netherlands in greenhouses because they were Venlo greenhouses that had a lot of ventilation and a lot of CO2 was escaping through the windows. Now with the new technology greenhouses, and that's why I'm so happy with also, let's say, the new inventions that are coming out and the combination, like the rest in our lives. There's not only one solution. It will be a combination of different solutions. So I think the solution CHP, creating an additional income stream, creating CO2, but sometimes you cannot use the CO2 anymore because the ventilation in the greenhouse is too low. Then Camille kicks in with the air capture system that is food grade CO2. So, it will be a combination of different things that we will see and face in the future.
Thank you. Also want to remind the audience that you will get an email which will have the recording of this webinar and the deck and a copy of the Google slide deck. Also want to give a shout out to the state of Pennsylvania. Mike Roth is posted in the chat that Pennsylvania currently has a grant to support CEA utilization of on-site CO2 as well as co-location support. So I just wanted to, and there's a link that Mike Roth has put in the chat. So I want to check that out. Okay, we'll move on to our next question. Someone has a concern that they ask, why these cannot be closed systems that do not allow the escape of the used CO2 from closed growing facilities.
I think that's more of an operations dynamic. I mean, they try to make, at least for indoor cultivation, the rooms as sealed as possible, but CO2 leaks out of doors, out of walls, out of HVAC systems. So they try to keep it all in there, but it's still one of the main users of CO2.
Thank you. All right. Next question is, why not just blow outside CO2 at 400 parts per million? Why not just blow outside CO2 through the greenhouse like Kubo Ultra Clima, which is a kind of a greenhouse. It's a semi-closed greenhouse. I guess I'll take a stab at it that the point that would help if you bring in 400 part per million, that'll help keep it at ambient, but you want that you get a lot of benefits out of elevating it in yield, or you can also use enriched environment of CO2 as kind of a trade for light and for heat. You can pump in the CO2 and get a better yield without paying for lighting or heating, which is much more expensive than generating CO2. Any of our panelists want to take a stab at that?
Yeah, I think, it's a good question. But basically you want to put only CO2 and not all the outside air also in the greenhouse, because, you need a lot of volume, because in the outside air, the percentage in a cubic meter of air is just very low. So you want to capture the CO2 out of the air and concentrate it and then blow it into the greenhouse through our systems. The point is also in the winter time, you do not want to pull this air into the greenhouse because you want to heat the greenhouse and not cool down the greenhouse. So I think to concentrate the CO2 and to get clear CO2 in the greenhouse is the way to go, because you want to keep the greenhouse out of stress as much as you can, and you want to have an even climate, an even CO2 dosing system. The CO2 has to go everywhere and basically not mixed up with air. So I think that should be the answer to the question.
All right. Well, thank you. We have lots of questions we didn't get to. I apologize for that, but we do need to sign off today to respect everyone's time. We want to thank Camille and Dick and David for their expertise that they shared with us today. I want to thank my colleague Brennan McMillan for helping out today. We've put the emails in the chat that you can reach out to the three of them to discuss these questions that you have or other opportunities that you're interested in learning about. With that, I want to sign off today, and thanks so much for RII for joining our webinar.